brain is dead right now. Yeah, that happened to me. That was it. We had all that for a while.
Oh, yeah. Here, come on, I want to use this. Sure. Thank you, sir. Sit down. Look at things. Come on. You know what? We can do it right here. I'm going to go in the hallway. It's quiet.
Can you skip airplanes?
Huh?
We can skip airplanes?
Is the faster room really trying to figure it out?
talking about what we're talking about, and doing it the same way, it's great. This class is taught.
Yeah, that's cool.
It's taught to two or three different participants. And then you also do exercise.
I think so.
There you go. Right now, I'm just teaching this code. Summer, I teach technology, STEM. Which one? 20. So it's combined. Intro.
Except as it in counts.
So it's very cool to look at questions this directly. Yeah, I think
Probably a little later. I'm not sure when I get started. Probably do some sort of. Yeah. It just got chill. Yeah. I got chill real quick in here. That's like 20 degrees. Gotta catch me before everybody leaves. Yeah, because
Maybe
you
I
have
want
a
a
500 gigabyte. I would not, I would, if Dream is in this class with us, I would not make any good grades right now. It's really good, I think it would be so hard for me to concentrate with Dream. Because every time I go to the store, it's a lot of shit.
If I can figure it out, I can figure it out.
Okay.
That's all right. So we have, right now, learned how to name ionic compounds and molecular compounds. The last thing we have to learn to name are acids and bases. Acids and bases are going to have their own lecture at the end of the semester, so we're not going to talk too much about them right now. But we're going to talk just the very basics of them so you know what an acid and a base are, and then also how to name them. Acids and bases, number one, are ionic compounds. And so because they're ionic, when you dissolve them in water, they're going to break up into their ions. If we put an acid in water, we get the ions that come from it. An acid is going to make hydrogen ion. That's what makes it an acid. Acids make hydrogen ion, and so they contain hydrogen ion. They are essentially an ionic compound where the positive ion is hydrogen. So this is hydrogen chloride, but you put it in the water and you get that. And that's going to have a different name as the acid versus just hydrogen chloride. H plus doesn't like to exist though. You're never going to have a beaker of acid, you reach in and pluck out an H plus. As soon as that H plus forms, it latches on to a water. Now, if we have water, H2O, and we add a hydrogen to it. So we have water, we're going to add our hydrogen ion. If we take H2O and add a hydrogen, what do we have? H3O. Here we have no charge. We add a positive charge. What is the new charge?
+1.
+1. 0 plus 1 is +1. And so H plus, when it's in water, is actually H3O plus. And so people like to use these two interchangeably. In reality, this is the correct way to write. You're not going to find many people who are going to mark you wrong if you put that. There may even be professors who teach that. But we are learning that. Okay? This is called hydronium ion. That's not something I'm going to ask you, this is hydronium ion, but that's a term that I'm going to use over and over and over again, especially when we get to the acids and base lecture. And so this is equivalent to that. They really are interchangeable. A base, when you put it into water, you make an aqueous solution. Oh, sorry. Okay, what they're saying is bases react with acids to make water. So let's think about this. If you have an acid that gives you that, you need to react it with something to give H2O. What two elements have to be here? H, you're going to need another hydrogen, and you're going to need an oxygen. And what is the charge on water? 0. Hydrogen had a plus, and so what has to be the charge on that?
-1.
-1. And so a base is always going to make this, and it's actually write it OH negative. This is called hydroxide ion. That's on your polyatomic ion table. So acids make H plus or H3O plus. Bases make OH minus, hydroxide ion. So here, this is sodium hydroxide, but it's an ionic compound. We have sodium, we have hydroxide. You put it into water, you get sodium and hydroxide. So now you have the hydroxide that's floating around, and you can react with the H plus from an acid if you mix an acid and a base. Yeah?
So as soon as we see an H, we can say that it's an acid, and as soon as we see an OH, we assume it's a base whenever we're doing that?
Yeah, as long as the H is in front, so it's a positive ion. Because if ammonia, you have an H, but it's not an acid. Because those hydrogens aren't acting as a positive ion. So hydrogen chloride is hydrochloric acid. It acts just like an ionic compound between hydrogen and chlorine. This is HCl. You put it into water, it breaks apart. Our chlorides are floating around, but the hydrogen ions, immediately grab onto a water. And so you don't see hydrogen ions floating around. What you see are the hydronium H3O plus ions floating around. And so if you look, there is one of these for every one of these. Because there started out to be 1 in 1. Bases do the same thing, but we don't always have OH directly in the formula. So ammonia, this ammonia that you use at home, is NH3. Ammonia is actually a base. We'll talk about it more in the acid-base lecture. This is what we call a weak base. That's not something you need to know now. But you look at that, and you say, well, it has no OH in it. So how can it be a base? The trick is, and the key is, bases form hydroxide ion when they're put into water. And so sodium hydroxide, when you put it into water, it makes hydroxide ion just by breaking apart. It doesn't have to do anything fancy. But ammonia is not an ionic compound. And so it can't break apart, and even if it did break apart, there's no OH to form. But when you put it into water, it reacts with water to make ammonium and hydroxide. And so what it does is it steals one of these hydrogens. Here we have H2O, it plucks it away, now we have NH4. If you take a hydrogen off of water, what's left is hydroxide. This is a reaction, not a reaction you need to know at this point. I'm just explaining how you can get a base from something that doesn't have OH in it. It's going to react with water, and then in the process of reacting with water, it'll make hydroxide. So just like we had oxo anions, we have oxo acids. So an oxo acid is an acid where the negative ion is an oxo anion. And so this is the acid with hydrogen as our positive ion and nitrate as our negative ion. And this is called nitric acid. Hydrogen with sulfate is sulfuric. Hydrogen with carbonate is carbonic. We'll come back to the names. And then this is acetic acid. That's vinegar. This is probably the most complicated acid we're going to deal with this semester. And we're not even going to even barely scratch the surface of this. There are all kinds of mathematical formulas and stuff that go with an acid like this. But essentially what's going on is if we take acetic acid and we draw it out. So when we draw a formula, these little lines are bonds. And so it's showing that these hydrogens are bonded to that carbon bonded to that carbon, the oxygen to that carbon, and so forth. If we look at acetic acid, this hydrogen right here likes to come off. The other ones are stuck in place with superglue. But that one can come off when you put it in water. And so acetic acid, even though it is not really an ionic compound, when you look at it, it can act as an acid because that hydrogen can come off. And we'll come back to this more later on, both in lab and lecture. So here is another list of names and formulas. And we're looking for a pattern in the name. And so let's start, number one, with just these first four. Just these first four. Do you see a pattern of how they are named? Correct. They all start with hydro. Say hydro, and then you say essentially the first syllable of the second element, hydrofluoric acid. Hydrochloric acid. Hydroiodic acid. Hydrosulfuric acid. If you have an acid, it just hydrogen and a halogen, and so fluorine, chlorine, bromine, iodine, or astatine, which you're never going to see astatine. It's just hydro, first syllable, ic, acid. Same thing if you have something like sulfur here. And so if your negative ion is an element, it's just hydroic acid, fill in the blank between the hydro and the ic. So those are easy. Where it gets a little trickier is when we look at the acids made with polyatomic ions. And so there are a number of them up here. And this slide, you only need to know the ones that have asterisks. For the ion table, I said you didn't need to know the ones with the asterisk. For this one, you do need to know the ones with the asterisk. And note there's 2 extra that I added down at the bottom here. And so there's really only 4 of them, and the 4 of them are 2 pairs. So like with the nitrate and the nitrite, if you can remember one and then the rule, you know them both. So let's look at just these 2 pairs and see if we can find a pattern. So look at sulfuric, sulfurous, nitric, and nitrous, and think about the names of the polyatomic ions that are in them.
Us is one less oxygen.
Yes. The us has 1 less oxygen. And so what is SO4 named? That was sulfate. If that's sulfate, what's that? Sulfite. That was nitrate. That was nitrite. If you have an acid with an ion that ends with 8, it's going to become an ic acid. If you have an ion that ends with ite, it's going to become an us acid. So eights become ics, ites become us's. So if you remember, sulfuric acid, sulfurous acid has one less oxygen. That's, again, how I do it. If I walked out there and somebody asked me what nitrous acid is, I would think nitric acid is HNO3, so nitrous acid is HNO2. I memorize as little as I have to. I had to memorize the rule, and so why not use the rule? And so you have to know sulfuric acid, sulfurous acid, nitric acid, and nitrous acid. You need to be able to go back and forth. Whether I give you the name, give me the formula. If I give you the formula, give me the name. Now I want to point out, there's two of them up here that look very, very similar. Hydrosulfuric acid and sulfuric acid. Why is that hydro very, very important?
Maybe it's strongly bonded to the hydrogen?
Well, I think you might be overthinking it. There are two different things here, right? H2S and H2SO4. Those are two very different things. And the only difference in the name is the hydro. And so that hydro tells you that it's H with sulfur, not H with a sulfate. If there's a hydro, you know it's just hydrogen with an element. And so you don't have to worry about the eights, the ites, the ics, or the us's. It's just sulfur. Hydrosulfuric acid. And again, I remember hydrochloric acid. That is my base. If I have an acid that is H with an element, go back. Well, chlorine is hydrochloric acid, so it must be hydrofluoric acid, hydrobromic acid. You can always come back to a starting place that you know you're correct, figure out what the rule is, and then apply it to the formula that you're dealing with. Again, here's another flow chart. What's the name of that? Hydrobromic acid. Let's going to skip that one for now. We'll come back to it. That one. Phosphate is PO4. So what is, if phosphate is PO4, what is PO3? Phosphite. And so if the acid made from phosphite, it can't be hydro. Hydro means it's just with an element. And so do we know there's no hydro? Phosphorus. I have the names. Yeah. Phosphorus acid. Now, the second one there. SeO4, that's not something you'll ever see again. I don't think that's on your table. SeO4 is selenate. So the ion is selenate. What's the acid? Selenic acid. Eights become X. And so you didn't know what SeO4 was, but as soon as I told you it was called selenate, took the 8, make it an ick, you know the name of the acid. You don't even know what this is, but you can name it. Yes?
Why don't we incorporate like something into the name when it has to do with oxygen? Because they don't all have to incorporate oxygen. Like hydrobromic.
So you're saying, say it again?
So why don't we like kind of have something else with it to say that it has oxygen?
Because we know it was ick, we know, because it's ick, we know it was an 8, and then it's up to you to remember what selenate was, that it had oxygen. Sometimes there's that little thing, well, we are going to assume that we're going to make our students memorize this, and so let's base everything off that and make them memorize that. But I didn't make the rules. I'm just a messenger.
Yeah, that makes sense.
So what's that called? Hydrochloric acid with number 2. Nitric. There's no hydro. This is nitrate, and so it's nitric acid. That's one of the ones you have to know. So that's nitric acid. That is nitrous acid. What's that one? That's sulfate.
Sulfic acid.
Sulfuric acid. Sulfuric acid. And so what's H2SO3? Sulfurous acid. Make sure you know nitric, nitrous, sulfuric, sulfurous.
What if we kind of spell it wrong? Would you mark it wrong?
As long as I know what you're saying, it'll be right.
Like what if I said sulfic?
I would mark that wrong.
Okay.
But if you spell sulfuric in the old-timey way with a crooked K on the end, I would mark it correct.
Is that the German way?
No, that's the cartoon way.
Oh, okay, yeah, I was thinking K like.
Actually, not to mention it, I bet you the Germans do spell it with a K. I bet you they do. Okay, is this the last slide?
Yeah.
It's definitely the last idea.
It is.
Okay, the last thing we got to talk about is molecular weight. Wow. So, yes, last week before, we talked about atomic weight. So we said the numbers up there on the bottom are the mass of one atom of that element. Now we've made molecules. And so we can find the molecular weight. So the atomic mass is given by the periodic table. In order to get the molecular weight or the molecular mass, all we need to do is add up the mass of all the atoms in it together. Whatever they equal, that is your molecular weight. So if we wanted to find the molecular weight of a hydrogen diatomic molecule, H2, we just say, well, each hydrogen is 1.01. There are 2 of them, so times 2 is 2.02 AMUs. We're still atomic mass units because we're just taking it off here, and those are AMUs. If we take AMUs and just multiply by 2, they're still AMUs. So what is the formula for sodium chloride, NaCl? The mass of sodium is 22.99. There's 1 of them, times 1, plus the mass of chlorine, 35.45, times 1. Add them together, 58.44. We're not done yet. So somebody give me their favorite non-metal.
Oxygen.
Carbon, I heard oxygen. Nitrogen. Chlorine.
Sulfur.
Sulfur. Phosphorus. Either other people have caught on to what's going to happen here, or we have some gluttons for punishment.
Tell you.
So now somebody tell me their favorite number between 1 and infinity.
6.
6.
1.
1.
2, 3.
2, 3.
2, 4.
2 and 4. I heard an 8. Let's go an 8.
Oh.
So we now have to find the molecular weight of that molecule. But the bigger it gets, the more work it is, but it does not get more difficult. It is not more difficult to do this than sodium chloride. And so we're just going to take carbon. Carbon, we're going to round it to 12. If you look it up there, it's basically 12. 12 times 6 equals something. Oxygen is 16 times 1. Nitrogen is 14 times 2. Chlorine, oh, I put that. It's going, oh, that 3 goes here.
I was gonna tell you, but I didn't want to correct you.
Well, if I put the 3 there, that's actually 3 carbons and 1 iodine, right? And so we just make it easier. So chlorine is 35.5 times 3. Sulfur is
32.064.
32. 32, and there are 2 of them. Phosphorus, I don't remember phosphorus at all. What's phosphorus?
Phosphorus is 31.
31.
31, and there are 8 of them. We don't need to go through. Is there anybody who is not comfortable going 12 times 6? Anybody not comfortable going 35.5 times 3?
Not on my copy.
Do them all, add them up. Whatever you get, that's the molecular weight of that beast. Right? It doesn't get harder, it just gets more work. Is there anyone that's not comfortable calculating molecular weight? Okay. Questions on anything we went over today?